the sea of love.
In problem 2136, we are supposed to find the point P where the total electric field is zero. First of all, this negative charge will have electric field pointing this way towards the charge, and the contribution from the positive charge is in this direction, pointing away from the charge. So at the point B, we have two electric fields, and at some distance they will cancel each other, and we are supposed to find what is that distance, x. Let's define our positive direction to be to the right. In that case, the electric field produced by the negative charge is positive, and let's call that E1. It is k times the magnitude of the charge divided by the distance between these 2 points, which is x, and the distance squared. In the case of the field produced by the positive charge, we see that it's in the negative direction. So we have E2 equals minus k times the magnitude of the charge divided by the distance between them squared. So if we call this distance here d, 12 centimeters, the total distance from here to here is d plus x, and that squared. Note when I said the magnitude of the charge q1 and q2. So by q1, for example, I'm meaning the magnitude of minus 25 microcoulombs, which is 25 microcoulombs, and for q2, magnitude of plus 45 microcoulombs, which is 45 microcoulombs. We take the magnitude to be positive, or we calculate, or we use only the magnitude, because we are taking care of the direction of the field by our sign convention. In this case, negative because it's to the left, and in this case positive because it's to the right. If we would put the actual values of the charges, especially in this case when q1 is negative, we would end up having our E1 to be negative, but that is not the case. It is positive, it's pointing to the right, and we are safe when we are using magnitudes of these charges instead of the actual values. And now we are ready to find the total electric field strength at point P. So it is simply E1 plus E2, which is k times q1 x squared minus k times q2 divided by d plus x squared. So we cross multiply to have the same denominator, and we get q times q1 d plus x squared minus this times this, x squared times k q2, and the common denominator is x times d plus x squared, and we want this total field to be zero. So here we have the equation that we have to solve. We don't have to care about the denominator, we're only interested in this numerator because that's the only one that can take this expression to zero. Let's make it look nicer first. So they both have the factor k in common, so we can take that one outside. And then we expand this term, so it's going to be q1 times x squared plus 2 times q1 times dx plus the last term d squared times q1, so q1 d squared, and from here we get minus x squared times q2, and we don't care what's below because the denominator can't bring this expression to 0. So when is this 0? Let's take this expression and continue from here. So this is a second order equation, and let's collect the terms. So x squared times q1 minus q2 plus 2 times q1 d times x, and then we only have the constant term plus q1 d squared, and this has to equal 0. So we use the quadratic formula for solving x, minus b, which is minus 2 q1d plus minus b squared, so it's 4 times q1 squared times d squared minus 4 times ac. A is here, c is here, minus 4 times q1 minus q2 and c q1 d squared. And the whole thing divided by 2 times a, which is 2 times q1 q2 from here. We have our values. q1, that's 25 times 10 to the minus 6 coulombs. q2 is found to be 45 times 10 to the minus 6 coulombs. What else? D is 12 centimeters, 0.12 meters. And that's all. So when we plug these numbers in, we get two solutions. X is either minus 0.05 meters or 0.35 meters. We defined our x to be positive, so this one is no good. So our answer is x is 35 centimeters. And at that point, these two fields exactly cancel each other.
Do you remember when we met? That's the day I knew